Hello, I'm Anna Mackay, and this video is on optimisation in the Applied Calculus series. So we've got a few pointers here on how to solve applied optimisation problems. They might be handy, or feel free to skip them. Some suggestions: to read the question carefully and draw a diagram if applicable, devise a formula and think about the restrictions on x. If it's measurement, for example, it has to be greater than 0. Differentiate to find the first derivative when it's equal to 0. Do a sign diagram to show if it's a max or a min. And you may sometimes need to consider the endpoints because they might be the actual max or min. And answer in sentence form. So let's do two examples. The diagram below shows a rectangle ABCD and a triangle EAD. We're told that the triangle is isosceles, so we can put some markers on it there, and EAD is 90 degrees as is shown. All lengths are in meters. We need to show that the area of the figure is given by this formula here. So where to start with that one? Well, we've got two shapes, so sometimes it can be handy to name that shape 1 and shape 2. The area of the first shape, we're going to have length times by width, and we've got some values there. The area of the triangle though, half times base times height. So this would be our base and this would be our height. We don't know those though, so we might have to do some work on that. I sometimes find it handy to draw the shape that you're working on separately so that you can label what you know. We do know the length here though is 4x, so we'll call it that. Vertices are A, E and D. Being isosceles, we know that that line AE is also equal to this side over here, AE. So we're going to use Pythagoras to calculate AE. So you need to be quick with those sorts of skills as well as all your calculus skills. So AE squared plus AE squared is equal to 4x all squared. That's where the brackets come in handy. Collecting like terms and simplifying, 2 lots of AE squared is 16x squared. Simplifying further, AE squared is 8x squared. Then square rooting both sides. Just going to write the 8 as 4 by 2, just for some people that need a reminder of how squares break down, because the square root of 4 then becomes 2. So we have 2 root 2, and x squared square root becomes just x. So that's the length of AE. Now our total area is area 1 plus area 2. So I'll write that. Total area equals A1 plus A2. Sometimes it's a good thing to write what it is that you're calculating. So we'll add them together. A1, we now have to do the base times by the height. And so let's write that. We've got 4x times by 20, take 4x. And then we're adding on the area of the triangle. So that's half times by base, which is AE, which we've just worked out, times by the height, which is AE again. Now we're going to simplify each of these, expand this bracket to get 80x, take 16x squared. What happens here? The half and the 2 will cancel. This root 2 and root 2 will become 2, and this x will multiply with this x. So we will be left with, as I said, this 2 times by this, they'll create a 2. So 2 times 2 is 4. So we've got 4x squared. Collecting like terms, 80x, take 12x squared. And that's what we were asked to show. So we've done the first step. Moving on, we need to find the dimensions which maximize the area. So here is our area formula. So we need to differentiate first of all. So we've got A dashed of x is equal to, I'm just going to write out actually my A first, because I like to differentiate straight underneath. I find it easier to think about lowering the powers. So we've got 80, take away 24x. Then we set the derivative equal to 0. I also like to write what it is that I'm doing. equal to 0, and we're solving for x. So we're getting 24x is equal to 80. X is equal to 80 divided by 24, or 10 on 3. I like to leave it in exact form for as long as possible, just to avoid rounding errors. I'll put it in brackets though so that we know. But we haven't finished there. Just because we've solved for x, we can't stop there. We need to show that it's a maximum. So one of the techniques for that is to do a sign diagram. So here's our line for a sign diagram. We put on our critical value. Think about our domain. X is part of measurement, so it has to be a positive number. So we've got 0 there. But then how do we know if it's a maximum or a minimum? We should graph it. I'm not going to switch to my emulator this time around because I'll lose everything that's written on my screen. So you get your graphics calculator out and you graph that and have a look. Is it going to be a maximum or a minimum? I'll tell you now, it's a maximum. So that means the slope is increasing to start with and then decreasing. So we have a positive and then a negative there. But again, we're not finished. So I would like to say it's a max when x is equal to 10 on 3, but it wants the dimensions. So going back to our shape, we need those the 3 side lengths. So one of them was 4x. So where you see an x, you put in a 10 on 3. Now it's fine to round. The second measurement was 20 take 4x, and working that out to be 6.6, rounding to 7. And a to e, we've got 2 root 2x, which simplifies down to 9.43 meters. Now, often we answer in a sentence, a little bit tricky with the way this is done, so perhaps it would be more handy to draw a diagram and mark dimensions as shown. And we'll put on what we've got, 9.43 meters, 6.67 and 13.33. So that's our first optimization problem. Moving on. Doing a trig example. So we have a fence, AB is 2 meters high, and that's 2 meters from a house. A ladder, XY, touches the ground at X, and the house at Y, and the fence at B. L is the length X to Y, so this whole length here, and we need to show that L can be represented by this formula. So what do you do when you see a question like this? You need to be able to recall lots of other skills that you already know, and often when you see right-angled triangles, don't forget good old SOHCAHTOA. So that would involve 2 right-angled triangles. So let's see what we can find here. We have a first one here that's fairly easy to see. If we're wanting to find this length, the hypotenuse, we need one other length. Okay, we've got the 2 there, that should be fine. But where might a second triangle be? Well, you might start thinking, oh, okay, well, I've got the great big triangle here, and I need to know the length of that long line. I need to know one of the other sides. Well, the base here, I've only got 2 and nothing, and the height of the house, I don't know. So you have to start looking somewhere else. Think up here, you could imagine a triangle. So let's draw that in and see if that helps us. Well, that purple line would be 2 meters, so that could be quite useful. But we don't know anything about theta. Well, cast your mind back to the rules you know about parallel lines, because that line there and the base are parallel. And then this line here that transverses the 2 of them, we've got a theta there, so that means we're going to have a theta there, and that rule is corresponding angles. So let's draw these 2 triangles. I find that quite helpful to draw, again, the triangles you're working with, even if it's just a little sketch. So the first one we've got X to B, the next one we've got B to Y. Put in our theta, put in our known lengths, 2 meters on this one, 2 meters down there. And so that's an X. We want to know, let's call this L1 and L2, and we're going to add them together to get the total. Remember how to label a right-angled triangle. You've got the opposite and the hypotenuse on this one, and in the second triangle you've got the adjacent side and the hypotenuse. So we're going to use two different rules here. So let's start putting them together. The length of the full ladder would be L1 plus L2. So our length of 1 is opposite over hypotenuse. And what uses that? The sine rule. So we've got the opposite is 2 over the hypotenuse, which is, hang on, done that wrong. No, I haven't. Yes, I have. What I'm trying to do here is create an equation. So we've got the sine of theta. Whoops. Sine of theta is equal to the opposite over the hypotenuse. So we'll call that L1. Let's rearrange for L. We've got 2 on sine theta. And our second triangle, we have the adjacent over the hypotenuse, so we need cos. So construct a formula. Cos of theta is equal to 2 over L2. Rearrange. We've got 2 on cos theta. So adding them together, it wants it in this form though, so let's put L2 first. We've got L is equal to 2 on cos theta, add 2 on sine theta. So we've shown what we were asked to show. Moving on, we need to now differentiate to make it equal this. So I've put our formula here. So my first suggestion would be to make that with a negative power. So first of all, I would write 2 cos theta and all of that to the power of -1, and add on the other term, sine theta to the power of -1, and now differentiate. And it's dl by d theta. And using the chain rule, so bringing down that power, we'll have a -2 out the front, cos of theta, lower the power by 1 and differentiate inside the bracket to get negative sine theta. And the second term, bring down that power, so we'll have a -2 here, copy and paste the bracket, lower the power by 1 and differentiate the inside. Now if you want to go ahead and try and tidy that up yourself, go ahead. So we'll tidy this up. The negative power will go towards the bottom of a fraction, so we've got cos of squared theta, and I'll put the square there. The two negatives cancel here, so the numerator is 2 sine theta. The second term, we have 2 cos theta as our numerator and sine 2 theta as our denominator. But this is not in that form. You might want to fast forward in your mind and think about, well, why can't I just leave it there? What do we tend to do with these types of problems? We put the derivative equal to 0 and solve for x or theta. If you put that equal to 0 right now, that's going to be pretty tricky to solve. So putting it in this form where it's one term with a numerator and a denominator, that's going to make your next step much easier. So it asked you to do it this way, but if it doesn't do that, that's a good technique to remember. So what are we going to do? We're going to create a common denominator. So that's going to be, we could write that first if you like, cos squared theta, sine squared theta, slightly differing from the question there. So what do we have to do to this term to have sine squared theta part of it? We have to multiply by sine squared theta, which will make this sine cubed theta. So 2 sine cubed theta. And likewise over here, to make this term have cos squared theta as part of the denominator, we must multiply through by cos squared theta, which will make this cos cubed theta. I'll leave you to just rearrange those two terms there to make it match what was asked for. But we're essentially there. Just for time, I'm moving on. And now we're asked, what is the length of the shortest ladder xy which touches x, b and y? So that means we have our derivative and we need to do a sign diagram to show if it's a minimum or a max. So what are we doing? We're putting the derivative equal to 0. Now, you've got your derivative written on your page. I said 0, not theta. So when we're dealing with fractions, I'll just go back here actually, we need to set the denominator equal to 0 to solve. So let's go and do that. that is 2 sine cubed theta take 2 cos cubed theta is equal to 0. Now, don't be put off by this. Trying to solve here, we rearrange, try and simplify a little bit here. That cubed can be written on the outside of a bracket and the 2's will cancel. Oops, I mean to write a cube, not a square. So likewise, you could take the undo that cube, undo it, you know what I mean. So essentially what we're trying to find now is when is sine of theta equal to cos of theta. So some of you might just be able to know that, where in the unit circle that happens. I'm just going to quickly go across to our emulator over here. And so whenever you get these types of questions, graph them and create a visual for yourself. So we want to know where sine of theta or sine of x is equal to cos. Think about our view window. We want to be in trig. Let's just work with from 0 onwards because they're periodic, so they'll repeat anyway. So we want to know when they are equal. So that's where they intersect. So there's 2 points there in each period. So how do we find that? We g-solve the intersection. So you need to be able to recognize the y values. 0.707 should key into your mind that's 1 on root 2. Heading across to the next intersection, we've got negative 1 on root 2. So these are the angles that we're interested in, and then they repeat. So going back to our question now, across here. Remember though, back in the question that we're dealing with, this ladder, think about the angles here. We want less than 90. So we only need that first one that we came across, which was when theta is pi on 4. Just going back because that's 1 on root 2 is equal to 1 on root 2. So you've got that written underneath where you had sine of theta equals cos of theta. And so we use that to finish off solving for L. So, but before we do that, sorry, we should draw a sine diagram. So where we put on our theta value and graphing L, if you were to do that, you would find out that it's a minimum. So that means we're going from decreasing to increasing. And substituting that in for L, we've got cos of pi on 4 plus 2 on sine pi on 4. Simplifying that, cos of pi on 4 is 1 on root 2. Same for sine, because that's what we were solving for when they were equal. Rearranging, we've got 2 root 2 plus 2 root 2 is equal to 4 root 2 meters. Go back and read the question. What is the length of the shortest ladder? And we answer in a sentence form. Therefore, the shortest ladder, excuse the messy writing here, is 4 root 2 meters, and you can leave it in that form. So that is the end of the video, but for some of my students, you might want some hints when you're doing 3G. If you don't, just move on and finish the video. For question 6, when you come across this, sine of 180 take theta, do remember that that is equal to sine theta. That'll come in handy. Question 8, you will need to use an identity, and I mean one of these identities. I'm not going to tell you which one it is, but refer back to this list. Another fact, if you're solving something like cos of 2 theta is equal to sine theta, do what we've just done on that previous question and graph it. Use y1 and y2, graph these two and see where they're equal, and recognize the y values and which fraction that relates to, if it's root 3 on 2, a half, or 1 on root 2. Question 9, you'll need to remember that pi is also equal to 180, and you can substitute that in, and that the angle subtended by, that should be an arc at the center is double. And what I mean by that is this rule here. So if you've got theta there, you've got 2 theta there. Very rough sketch there. So that's the end of the video and the end of the Applied Calculus series. Thank you.